morning, everybody. Welcome on our seminar, Quantum Information and Quantum Computing Working Group. This is the fourth seminar. Today, our guest is Víctor Daniel González Avella from Universidad de Antofagasta from Chile. And Víctor will tell us about quantum state tomography beyond 10 qubits. Víctor, please start.
Okay. Hello, thank you, Professor Wojciech, for the invitation. Today, I will talk to you about some quantum state tomography protocol. In particular, one what have been developed by my group in the Universidad de Antofagasta and Universidad Católica de Chile. So I will start with a little motivation about why we are interested in work on quantum state tomography in general, or of quantum devices, or how is the quantum computing evolving. Yeah, we know that the quantum hardware has been grown steadily in size and in complexity during the last decades. For example, here we have a roadmap of the IBM quantum processors. They are developing even each time bigger and bigger quantum processors. And this makes that the quantum devices and the study of the quantum process may be more complex. So we have these bigger 100 to 1,000 of qubits that are right now or in the near future. And in these cases, the study of the classical simulation of these systems becomes hard. It becomes infeasible. Yeah, in that sense, one of the aspects that we need to improve is the characterization of benchmarking of the multi-qubit hardware of the elements of the states that we are working on. To look for some applicability of these technologies, we know that they have the potential to improve several research areas, like, for example, cybersecurity. Yeah, we know that the classical cryptographic protocols in general relies on some tasks that are very difficult to do in the time that the communication between Alice and Bob lasts. Yeah, it's, for example, the ERSA algorithm, that in which we try to find the prime factors of a big number. We know that the security of this protocol relates on the fact that the task to find the two factors is very hard to do in the time that Alice and Bob are in communication. Yeah, but as I told, the security of these protocols relates on the hard to be the problem. If an eavesdropper find an algorithm that works quicker than the communication time, he can solve the problem before the communication ends and contain some sensitive information about, for example, our credit card number, etc. And the quantum devices or the quantum mechanics allows us to define some protocols that are secure by the quantum properties of the system itself, like the BBH84 and other protocols, in which an spy and eavesdropper will be detected instantly, so we can cut off the communication. But in some senses, we need to know that our protocol works well, that the states that we prepare to communicate are working good, etc., between several other properties. Also, the quantum devices, the quantum computer have been used in the last year to study some quantum chemistry. Yeah, we can simulate some molecules or prepare the states of a molecule in a quantum computer and study its properties. This is hard to do in a classical device, and as Feynman told, we are trying to study the quantum nature, the quantum properties of a phenomena in a quantum device, and a device that lives the quantum. We are not simulating, we are doing something that lives in a quantum world. So this will be improve the reach that we can achieve with this kind of study. Also, we can use quantum devices to solve some optimization and combinatorial problems like cubo problems, quadratic constrained binary optimization formulations, in which we can use some quantum device like quantum annealers to find the minimum of a function, to minimize some functions, and we find the optimal solution in a way that works quicker than the classical approximation for these problems. Also, in the last year, the quantum machine learning have been used continuously, or there, almost any approach to the machine learning has no quantum machine learning equivalent algorithm with different approach. For example, there's people that trying to find quantum data and test the algorithm on a classical device, or test some classical data like classifiers on quantum computers, and so on. And maybe this don't seems to be related directly with the tomography of the states, but in general, um, as I told you before, we need to prove that we are really preparing the states that we need to use, that the devices are working properly, and we can use the tomography to do so. Yeah, the quantum state tomography is the technique by which an unknown quantum state can be reconstructed from a set of measurements performed on an ensemble of quantum state. Yeah, we need an ensemble because once we measure one quantum system, we make a measurement, we obtain some information about the state before the measurement. But due to the collapse of the wave function or the postulates of the quantum mechanics, we cannot find more information in this same system, because if we measure again, we will obtain the same result. So we need to prepare a set of states that are our systems that are prepared in the same state. Yeah, that's because it's not possible to copy an arbitrary quantum system. Yeah, for example, we have this kind of Schrodinger cat state. If we measure once, we will find that the cat is alive or is dead. But if we measure again, this won't change in general. Yeah, at least unless we made some applies another operation over the state after the measurement, but it's not what we want. So we have to prepare a set of or an ensemble of systems, prepared identically. In the sense of measurement, we work for this work, we use some projected measurements or von Neumann measurements. We have a set of projectors that are orthogonal between them, and they sum up to the identity. Yeah, this is the simplest class of measurement that we can apply, and are described by some observables. Yeah. In particular, we're interested on systems formed for n-qubits, for a certain number of qubits, which the dimension is 2 to the n, when n is the number of qubits. In general, the standard protocols to perform quantum state tomography for this system requires to measure all the 4 to the n chains of combination of local Pauli operators and identity operator, and then apply a maximum likelihood estimation algorithm to obtain the best candidate for the state that we are reconstructing. Yeah, this is like the most standard method that we can apply. But if we do some considerations about the measurements, the set of measurements that we want to apply, we can reduce this number in some ways. For example, if we use a symmetric informationally complete positive operator valued measures, we can reduce this number to d squared total measurements. This means these SIG PUVM are sets of equiangular lines or equiangular states that conform a set of d squared equiangular lines in dimension d. These sets are conjectured to exist in any dimension, but haven't been found in all of the dimensions. And in general, in the lab, can be very difficult to implement because this will need some resources that are expensive to implement in the lab. Also, we can use complete sets of MUVs. In this case, we are treating with qubit systems. So we need a total of 2 to the n times 2 to the n plus 1 measurements. one set for each basis. These sets, for the case of qubit system, are found. It can be found, but in general, for any dimension d, these sets are. We don't know if these sets, complete sets of MUB, exist. And in depending of the system, these can be also expensive to implement because they may require some entanglement. Depends on the specific set or mutually unbiased basis that we are using. If we have, on the other hand, if we have some information a priori about the state, we can use this information to reduce the number of measurements. For example, if we knew that we have a mixed state of rank R, we can make use of the compressed sensing. If this R is much smaller than the dimension of the system, we can use this to only apply a total of the order of R times 2 to the n logarithm square of 2 to the n measurements. So we can reduce the number of measurements that we need to apply to obtain the state reconstruction. Yeah. Why we need to apply this lot of measurements? We need to have a different perspective of the state, because if we don't have enough perspective or different projections of the state, maybe we can reconstruct a part. But remember that for quantum systems, we are working with complex number, so we don't have directly access to the phases of the coefficients of the state, for example. So if we miss some part of some measurement, we can find we can have mistakes in the reconstruction. And if we have some kind of we miss some perspective, we can get to errors and get a little bit offended depending of the angle of we see the problem. So another example is that if we have a system which state is a product state structure, or some permutation invariance, we can also reduce the number of measurements that are required. Yeah. In general, these methods works well, but requires a lot of post-processing because they don't fully reconstruct the state. We find an estimate, and then with the use of some maximal likelihood algorithms, we achieve the best candidate state. Yeah. There are some cases, for example, when the state is pure. Yeah, if the state is pure, and formed for an n-qubit system, in our case, we can estimate, it has been proven that we can estimate the state with a total of m times n plus 1 measurements basis, with this m to be at least 2. Yeah, it does not need a lot of post-processing to reconstruct the state. Yeah, let's suppose that we have a state of writing in this lexicographical way. So if this is the state decomposed in the computational or the standard basis. So when we want to reconstruct the state, we need to find the 2 to the m complex coefficient C here. So this method that use local measurements here was developed by Pereira, Zambrano, and Delgado in 2022. It's an iterative algorithm. They start to reconstructing some substates of the system, starting with substate of 1 qubit. They find this state up to global phases, then use the set of states to find some relative phases between these substates, and go to find substates of 2 qubits, and so on, until they find a state that is equivalent to the state that they want to reconstruct up to a global phase. Yeah, it's like they start to knit together the parts of the state and finally find this state or this candidate up to a global phase that can be found in some post-processing process. Yeah. So this method uses only local measurement, but the reconstruction is iterative. Yeah, we need to do a lot of calls to the same algorithm to work with to find the final state. Also, on the other hand, we can use for any d-dimensional quantum pure state, we can unambiguously reconstruct it by using only 5 observables. That is, with some projective measurements on 5 orthonormal bases. Yeah, this method has been proposed by Professor Goyeneche et al. In 2015. And this is a method that is robust against experimental errors and requires some simple post-processing based on statistical interference. Yeah, they propose these 4 bases here, in which each basis element relates 2 elements of the state or the computational basis. This addition here of the element is carried out modulo D. This means that when we achieve the D plus 1 element, we start with the 0 again. The 4 bases here are completed with the computational basis. So the computational basis gives us the square of the absolute of the amplitudes of the coefficients. And we use the 4 bases to find out the phases of each element. Yeah. For this, we define these probabilities, this p plus minus k or p plus minus tilde k, to be the projectors on the basis element k plus minus k plus 1 and k plus minus I plus k plus 1. So with this information that we obtain from the probabilities, we can use or define the probabilization identity for this complex amplitude. Is here 4 times this product of 2 elements that are the ck and the ck plus 1 are equal to this sum of elements. If we look carefully, these elements are the same that we obtained from the projection. They are the probabilities. And if we look carefully, each one of these equations allows to relate 2 elements, the ck with the ck plus 1, and this form a graph, a circle graph. So we have all the elements related between them to draw these links in a graphical point of view. So we can use this information to write down a system of nonlinear equations, and we can solve this system in an iterative way. Yep. So we can find with all these polarization identities and the normalization condition of the coefficients of the states, we can find out all the amplitudes and the phases of the state and make a reconstruction. So we have this protocol that use a small number of measurement bases. We have, in that sense, a total of d times 5 d times 5 measurements, and we can reconstruct almost every state. There is a subspace of a pure state that cannot be reconstructed by this method. If we can see it graphically. We have this. If some of the element are 0, for example, we have 2 elements that are 0. They are not in the graph. Each element that is 0 won't be present in the graph. So if 2 of these elements are 0 and are not consecutive elements, for example, the 1 and the 3, we lose the continuity or the way to reconstruct this state iteratively. So we have to go to a subspace and find the new graph and make the reconstruction in the subspace and then go again to the full space. Yeah, in that sense, we can find this null measurement subset of the pure state. But we can solve the problem going to this subspace and make the full reconstruction of the state. This method had a problem that some of the measurement required to make use of entanglement, that, as I told you before, the entanglement is an expensive resource to do in general for big systems, or in general to implement entanglement states in the laboratory is not so easy. So we have to try to find some protocols that don't use that use only local measurement. And that's our proposal. We propose to perform a method or a protocol that uses a set of two n-separable orthonormal bases along with the computational basis to do the state reconstruction or the state estimation. Yeah. In our case, the bases are constructed in the following way. In general, we start with the computational basis that can be seen as we measure all qubits separately in the computational basis of each subspace. And then we start to apply a set of measurements. That is, we measure all qubits but one in the computational basis, and the left, the one qubit left, are measured in the using this transformation. This transformation can be applied the Hadamard matrix or this product of the S times the Hadamard matrix. If we see the columns of these matrices, this is the basis given by the each. If we take the columns of vectors or basis elements, this is the basis of eigenstates of the Pauli X observable, the Pauli X matrix, and this one is the basis of the eigens formed by the eigenstates of the Pauli Y matrix. Yeah, for example, for 2 qubits, these are some of the bases. We have the basis, for example, when we have the Hadamard matrix on the right, we have these bases. We know that we note that you can note that these relate two elements. For example, the zero, the first element to the second, or the first element to the third, the second to the fourth, and so on. If we have 3 qubits, we add the bases with the H in the left, in the center, and the right, and so on, and the bases with the product SH. That are the same structure, but the lower row with ones and minus one will be I and minus I. So in the sense, similar to the previous protocol I showed you with the phase measurement, we here can establish some relations between the elements in the same way. I will start to telling that each basis element can be represented by this expression here. We relate an element k, a number k, 2 to the pi p plus 1 plus j, this equation here, where p is the position of the product of the Hadamard or the S Hadamard product. Yeah, starting numbering from the right. Yeah, this will be the position 0, this will be the position 1, and this here will be the position n minus 1. So we can use this expression to find all these elements, or are the basis element, or are the measurements, predictive measurement that we will implement in the protocol. And as the same that we seen in the previous protocol, we can associate this construction to a graph. In particular, in this case, we can associate the structure of the problem with an hypercube or a cubic or hypercubic graph. In that sense, the connections, each element of the state of the computational basis represents a node, and the edges are given by the elements related through the bases or through the polarization identity, maybe, when we can see it in that way. To see which elements are connected, an easy way to do is we can decompose the index, the J, K index, etc., in a binary string. For example, for 3 bits strings, we have the 0, and it is connected to each element to which the Hamming distance between them is 1. This means that if we take the two bit strings and compare each element by element, they differ only in one element. For example, the 0 is connected to the 1, to the 2, and to 4. These are the... if we look carefully to all this structure, we find cubic structure for the elements. So we have this cubic structure, and if we go to 4 qubits, for example, we have this hypercubic structure, and so on. We will, if we go to 5 qubits, we have 2 of these cubes connected, and so on. And this give us some advantage. The first one is that they appear several
Sorry,
times.
may I have a question?
Yeah.
How does it, because I'm lost, I must admit, does this mean that every qubit introduces a new dimension in this visualization?
Yeah, every qubit introduces in general a new dimension. This is a n degree hypercube for n-qubit system.
Okay, so if you go back, please, to the previous slide, then we have a standard three-dimensional. The next one, the standard three-dimensional cube. On the next slide, which is depicted. So, how should we understand? How should we understand the vertices? So what does it mean that what is the vertex? This black dot, vertex, black dot.
The vertex are, we can see the vertex are the different elements of the computational basis. 0, 1, 2, 3, to 8, to 7 in this case.
So these are 3-qubit system because we have 8 possibilities, okay?
Yep.
Okay, perfect. And on the next slide, we have 4-dimensional
hypercube. 16, exactly. Yes.
Yeah, so 16 possibilities. So we have
2 to the power of 4, exactly. Okay, thank you very much.
Okay. Yeah. So we have some advantage in that sense because we find we now have plenty of paths between any 2 pair of nodes. This is a Hamiltonian structure graph. We can find a Hamiltonian path between any 2 elements. And this allows us, for example, if we have some zeros, if the graph remains connected, we can find roots between any pair of nodes. In that sense, with the use of the polarization identity, here we relate 2 elements. The elements related are given by the basis. And we have to find the best path. To do so, we first make the measurement in the computational basis to find the absolute square of the all the coefficients. And then we associate this amplitude with the weight of the vertex in the graph. Then we select the vertex with the highest amplitude, with the highest value, to be kind of a target or a root node. And all the other, the iterative way to solve the equation system is each other node has to find its path to the root one. Let's say, for example, I want to go to this in the down left corner, from this here in the upper right corner. So I have in this case for three qubits, they are the farthest. They are the farthest element. For example, they are both the opposite corners of the cube, and they have a total of 6 different roots of the minimal possible length. In general, for the 2 farthest nodes in the cube, for an n-degree hypercube graph, there are n factorial roots between the 2 elements. So we have to decide which one is the best. Any of the roots of the path work well, but if we select some properties of the root, we can find a higher fidelity. Yeah, this improves the fidelity of the final reconstruction. Yeah, for example, I can go through this red path or through this yellow path. For now we have been selecting the roots of the parts that pass through the nodes with the highest total weight. See, I decide to go to the root, to the path that maximizes the sum of the amplitude or the weights of each, or all the path or all the nodes that we pass through. So as a start, we find the best root and make the reconstruction iteratively and find the amplitudes and the phases of the state. To test our protocol, we have made use of the quantum computers from that are available free on Quantum IBM platform. In particular, in this moment, we have tested this protocol in the IBM Sherbrooke, IBM Kiev, and IBM Kyoto quantum computers, and we have prepared some states up to 10 qubits. It's our biggest system right now. So in that sense, we need to prepare the system, but we know that these quantum computers of IBM are NISQ, are noisy, are very sensible to errors due to coherence time or to some other noise, etc. So we try to find the best way to implement the best candidate states to implement the protocol, and we have found this structure of states. These states are related to the graph state construction. In that sense, we have made use of states prepared with a fixed depth, regardless the number of qubits. And from these three layer states, we have a layer of only local operations to put the qubits in a superposition state. And two layers of bipartite gates or bipartite operation over the pairs of qubits, starting with the pair qubits and then with the odd qubits number. And this gives us a state that is genuinely entangled. The elements are genuinely entangled between them. And as we are using a shallow depth, they have a good accurate construction. And we have using with this operation the square root of x or the ICR gates, because they can be implemented directly by the quantum processors available right now in IBM. Because as we know, we used to do this entanglement process with CNOT gate, for example, but the IBM quantum computers available right now cannot apply directly a CNOT gate. A CNOT gate is composed by a series of pools that is translated to a set of gates. You know that they use a universal set of gates, and we can approximate any operation or any unitary operation or gate, etc., to a set of these universal gates. But these, if we use the CNOT or Hadamard gates or another kind of structure that is not in the universal set directly, we have to deal with increasing depth of the circuit. Also, the elements in the qubits in the quantum processors of this computer are not connected all to all. They have some connection in one direction between a pair of qubits. Also, we have developed an algorithm that look for the best qubit, the best connections, the qubits that minimize the errors. And this algorithm were a little bit better than the one given by IBM. And so we have this structure, we select the best qubits, and so we try to deal with all the possible errors to find the best reconstruction possible, or the best preparation to find the best reconstruction possible. So we start measuring all the elements in the computational basis. We measure all the qubits in the computational basis first to obtain all the amplitude, the actual value of the amplitude. And then we start to measure each qubit in the Hadamard basis. We measure this in the Hadamard is applied in the first qubit, in the second qubit, and the qubit, and so on. And then we apply the product SH. Well, in fact, we apply like the adjoint of this product, because we only are able to measure in the computational basis. So we apply the adjoint to make this rotation to the state, and then obtain the equivalent to the basis, give the desired basis of measurement. And with all this information, we use all of this information to reconstruct the state. So we do it iteratively. We send out of these measures. We started with 3 qubits, 4 qubits, 5 qubits and so on. We now have tested until this qubit, the 10 qubits, and we have found these results until this moment. We have this reconstruction with these elements given by the 3 quantum computers available right now. In this moment, we are making some measurements in Brisbane, another quantum computer, because Kyoto is no longer available, so we are not able to explore more on this computer. Right now, for these curves here, we have a few realizations because the access is limited. We have a time limit monthly to perform some experiments. So we are working on have more statistical basis to make better fitting of these curves. In general, we have worked with we can see that, for example, Sherbrooke is the newest one of the quantum computers. Kiev have been available in the last time, but it already exists before as a Byte computer, and they said that it's no free. So we have a lot of work to do in this sense to improve some of the results. Yep. But in our protocol, in these real devices, we have found that our fidelities are higher than all that we have found in the literature, with states that are genuinely entangled. Yeah, because we have seen some protocols that are applied to states that are products of Bell states or GHC states prepare in parallel, but no our elements are really entangled. So in that sense, is one of the highest fidelities that we have found in the literature, and we have, for example, in this work of Pereira, Zambrano, and Delgado, they found for 4 qubits GH state that is entangled, a fidelity or 0.875, and for 4 qubits we have fidelities above 95%. So it's an improve in that sense. So in summary, we have implemented a quantum tomography protocol that uses only local measurements and obtain a high fidelity state reconstruction. This is an advantage. In that sense, the number of measurements increase linearly with the system size. There is an improvement because we don't have an exponential growth like the standard protocols. And on the other hand, we have a explicit reconstruction formula and low processing cost. We only have to deal with this problem of the graph to find the best path between the elements. Is the hardest part of the post-processing step of this work. So in that sense, I think we have found a very good protocol. Is relatively cheaper to implement than other one because we only use local measurements, and in the measurements are on the eigenstates of the Pauli observables that can be performed in the lab. And we have some future work to do right now, like for example, improve the algorithm for the path construction. Yeah, we want to find a best way to implement this part of the algorithm to improve the computational time needed to do so. And we want to do this because we want to test on higher dimensional states. We are now working on 11 and 12 qubits systems, but we are limited through the access to the IBM quantum processors to go to higher elements. For example, we have in a free access account, we have only 10 minutes per month, and only one of these experiments requires around the 10 minutes, even a little bit more for 12 qubits, because we need to increase the ensemble size. Because, for example, for these cases, for 3 to 9 qubits, we have ensembles or 20,000 shots or 20,000 experiments for each measurement basis. And for 10 qubits, we have used 40,000 shots per basis. And for if we go further to 11 and 12, we have to increase this number of shots to find good reconstructions. Yeah, in general, this is almost all I have to share with you today. We are looking also a way to improve this protocol in general, or to find new protocols that reduce the number of measurements. We are now working on a protocol that make use of some local communications, local operation and classical communications to reduce the number of measurements necessary and the ensemble size. And it's promising, but the quantum processor doesn't work right now too well, the IBM quantum computers, with this kind of intermediate. We use intermediate measurements to decide which operation apply to the different qubits. So there is these quantum processors are very noisy right now when we use this kind of structures. So we want to find a way to implement this, or try to find a way to reduce the number of measurements, maintaining that almost all the measurements to be separable ones. So this is all I have to share to you today. So thank you for your attention.
Thank you very much.
And
Thank you very much. Are there any questions or comments from the audience?
So have you tested, for instance, the fidelity between the stages you have, like with the one that you would like to have in the experiment, in terms of the how fast it goes to 1, in terms of the number of measurements you have to perform?
okay, I have tested that on the simulators, not in the real devices, due to these limitations. Specifically, for example, for 10 qubits, I have the first test was with 20,000 with less measurements, and the fidelity for 20,000 per basis was around 60%. So it's improved very very quickly with the number of measurements. Well, we have to double the number of measurements to have an improve of 20%. For example, for 12 qubit, I have estimated that I will need around 100,000 measurements per basis to obtain a fidelity of 85% around.
Okay, I'm asking this because there was this approach by Richard Kunk and collaborators about classical shadows, where they like randomly pick the Pauli measurements, and the convergence to fidelity of the fidelity to 1 is very quick with the number of measurements. I mean, they consume many less measurements. So can you comment on that?
Yeah, I have seen that there are several protocols that maybe work with less measurement. But for example, I know that for classical shadow, for example, we don't reconstruct the whole state. We only reconstruct like the properties that we want, and then make a post-process with that information to find the candidate states, for example. That's maybe why they work with less measurement, because they don't reconstruct all the parts of the state.
Well, I'm not sure. I think that the feature there is that they randomly choose the measurements, and somehow, like based on the information, they have an algorithm that wants to guess the state somehow.
Yep.
I mean, okay.
Yeah.
So
well, I have some protocols that use this information, but the algorithms are not close. I mean, they are iterative until they find like the precision they want.
Okay.
So they have to do this repeatedly, and the number and this maybe be very costly in the post-processing step.
Okay, thank you.
Do you have other questions? I can have one technical question. Victor, can you get back to this cube where there were 2 paths, or this one, exactly this one?
Yes, this.
I just want to understand how does it work? Does this do these paths, the red one and the yellow one, are they equivalent? Because there have many possibilities actually in here in this picture. So how can we distinguish the best one? Does it make any difference?
To distinguish the best one, as I told you, I assigned the amplitude of the different coefficients of the computational basis to the as a wave to each vertex or to each node. Then we have we find the shortest route or the shortest path between two nodes. And for example, for this example, we have 6 routes of length 3 between these two elements, these two corners elements. And we select the one that passes through the elements with the highest amplitude.
Okay, so this is the optimal
to maximize the total amplitude of the root, for example, the maximize the wave of the root.
Okay, so this is
that
how
is because as the wave at higher, the errors due to these limited statistics affect less the result. It's not fully necessary to select the best route because we can find good fidelities either, but the fidelity is improved if we find all the best routes.
Okay.
In that sense of maximizing the probability amplitude through the route.
Okay, thank you very much. Are there any questions?
Not from me. Thank you for the talk.
Okay. I can't see any more questions. Either there is nothing on the chat. Okay. Victor, thank you very much for delivering very nice talk.
Thank you.
Thank you very much.
Thank you for the invitation.
Goodbye.